Welcome to another exercise on the simplex algorithm. Here we have a slightly larger text exercise which goes as follows. The marketing manager for PepsiCo Gambia needs to decide how many social media and magazine ads to run during the next quarter. Each social media post costs $5,000 and is expected to increase sales by 300,000 cans. Each magazine ad costs $2,000 and is expected to increase sales by 500,000 cans. A total of $100,000 may be spent on advertisement. However, PepsiCo wants to spend no more than $70,000 on social media and no more than $50,000 on magazine ads. PepsiCo earns a profit of 5 cents on each can it sells. Now we have two tasks. First, formulate the respective linear problem, and second, determine the optimal number of ads to place in the next quarter. Well, of course, we need the respective linear problem to actually start with part B. So we're going to go right into it and start with the program formulation. So once again, the exercise text. And if we start with this, our first question is, what is the actual objective of PepsiCo? Well, they sell cans, they make money, they make a profit out of selling cans. So it's only natural to assume that as a company want to maximize their profit. Profit depends on how much advertisements they put in social media and in magazines. Because we can see here for social media posts, they sell these much more cans. For magazine ads, they sell these much more cans. And then, well, cans would be one possibility, but we're more interested in monetary gains, so we can multiply the number of cans with the actual profits in dollars they earn if we multiply these two numbers with the $0.05. Well, as I said, we have to decide how much ads we place on social media magazines, so we have two decision variables. Well, this leads to this formulation of our objective function, maximize profits. Profits is dependent on how much social media ads to place, x1, how many magazine ads to place, x2. For each social media ad, we have 300,000 times 0.05, so $15,000 profit. For each magazine ad, we have 500,000 times $0.05, so $25,000. Of course, those are relatively large numbers, which would make the calculation quite problematic. So we can shorten this down by a factor of 1,000. But we have to keep this factor in the back of our head, because at the end, when we get our optimal solution with a value for the objective function, we have to multiply this value for the objective function again with this factor 1,000. So keep this in the back of your head. And then we can continue after the objective function about our constraints. Well, first off, we have the constraint that we are not allowed to spend more than 70,000 on social media and no more on 50,000 on magazines. So how much does one social media ad cost? That's $5,000. So 5,000 times the number of social media posts should be less than 70,000. That's the first constraint we were going to add here. Again, that's quite large numbers, which would make the recalculation quite problematic. So we can just simply divide it by 5,000, giving us the much easier constraint x1 should be smaller or equal to 14. The same can then be done for magazine ads. So here we have 2,000 times the number of magazine ads should be smaller than 50,000. So this translates into this constraint, which can be made a bit easier by dividing by 2,000. So we get x2 should be smaller or equal to 25. So that's the first two, but we have one more. And that's the total budget we have for advertisement. Well, this translates into that the total costs generated by social media, so 5,000 times x1, plus the total costs for magazine ads, 2,000 times x2, should be no larger than 100,000, so should be less or equal to 100,000, which is this constraint here. Again, we could simplify this by dividing this whole equation by a factor of 1000, giving us then the constraint 5x1 plus 2x2 smaller or equal to 100. This problem looks much easier and much better to handle than this with those large numbers. Of course, for completion's sake, in the formulation of the problem, we also have to add our non-negativity constraints, meaning that we can only place 0 social media ads or 0 magazine ads, or a positive number, but no negative numbers. Well, so much for part A, for the problem formulation. So we can then take this problem and start to solve it. That's part B, solve this problem. And we're going to first build our simplex tableau for this by adding one column per decision variable. Here we have two decision variables. So we're going to have two columns. One row we add, the first one for the objective function. And then we're going to add one more row per constraint. So 3 constraints, 3 additional rows with respective variables. So this one represents the first, this the second, the third constraint. For the values we put into the table, we can start with the objective function. This is a maximization problem. So we're going to take the coefficients and multiply them with -1, since it's maximization. So we have -15, -25 as values here in the objective function row. And then, since those two are up here, we're going to insert 0 for x1 and x2, giving us, as a result, a function value of 0, which we place here on the right side. For our values here in the lower part, we're going to observe the constraints. So we first take a look for the values, the coefficients of x1. Here it's 1x1, here it's no x1, so it's 0x1, 5x1. So we have as coefficients 1, 0, 5, which we place in the x1 column. And for x2, well, here's no x2, so we have 0x2, 1x2, 2x2s. So we take the coefficients 0, 1, 2 and place them in the x2 column. And finally, we're going to take the values on the right-hand side and put them here on the right side as well. We can, well, use this process of just copying coefficients and right-hand side values because all 3 of our constraints are already smaller or equal to constraints. In this case, it's just copying the coefficients and the right-hand side values. So after having prepared this table, we have to check whether this solution which this table represents is actually a feasible starting solution. So we take a look here on the right-hand side. See, all values are positive or 0. Well, in this case, all positive. So we have a feasible solution and we can officially start simplex. This means we're going to take a look at those columns where we have a negative value in the objective function row. Well, in this case, both of them are negative. Then I'm going to select this column where the value is absolutely speaking the largest. Well, 25 is larger than 15, so this becomes my pivot column. In the pivot column, I'm going to consider the values down here, and I'm going in particular consider only those values where I have a positive value, positive element. So this one is omitted, and only those 2 are potential candidates for pivot element. How do I decide which one to take? I'm going to divide right-hand side value by this element. So I get 25 and 50 here. And then I'm going to select the row where this quotient is the smallest. 25 is smaller than 50. So x4 will become my pivot row. So pivot row, pivot column gives me as pivot element this one. Then I'm going to do my recalculation with this pivot element, which is displayed in the next table. So here I first exchange the variables in pivot row and pivot column, those two. And then I'm going to divide the pivot element, the 1 by pivot element, place it here at the position of the pivot element. So 1 by 1 gives 1. Everything in the pivot row gets divided by the pivot element. Well, since pivot element is 1, this remains the same. Everything in pivot column gets divided by -1, by minus the pivot element. So they just change signs. Well, they change signs. Then I have to recalculate all the other values. Here, however, I have a big advantage because in this pivot row I have a 0. If there's a 0 in pivot row, the respective column of this 0 can be copied as is. So this can be copied as is. And the same applies if I have a 0 in pivot column. Here there's a 0, so I can copy the whole row as is. So this one. Meaning we only have to recalculate 2 additional values, which is this one up here and that one down here. So if we consider this one, we can use this rectangle form or scheme for recalculation, which means we take this element and this element we consider as the opposing corner of a rectangle where the pivot element is the opposing corner. So those are 2 opposing corners in a rectangle, making it this rectangle with those 2 as other corners. And then we're going to take this element, the original element we wanted to change, minus this corner times that corner divided by pivot element. So in our situation, 0 minus 25 times 25 divided by 1. Minus minus gives plus, so we have 0 plus 25 times 25, which is 625. For the 100, we do the same thing. There we have this rectangle. So we go 100 minus 2 times 25 divided by 1. So 100 minus 50 gives 50. This gives us a new table. Now we can check whether this table represents an optimal solution, because once it's feasible, it will remain feasible, but not necessarily do we directly have an optimal solution after the first step of the simplex. The solution is optimal if all the values here in the objective function row are positive. Well, we see here there's still one column where we have a negative value, so we have to continue with our simplex. Well, this is the only column where we have a negative value, so this automatically becomes pivot column. In the pivot column, again, we consider all the values which are positive, which is 1 and 5. And to select which row we take for pivot row, again, we divide right side by this element. So 14 by 1 gives 14. 50 by 5 gives 10. Select the row which yields the lowest quotient, which here is this one with 10. So x5 becomes pivot row. So x1 pivot column, x5 pivot row gives us 5 as pivot element. So I'm going to switch then to the next slide and there do the retransformation based on 5 as pivot element. So I have this original table, do my recalculation by first switching the variables in pivot row and column. Then for the pivot element, I go 1 divided by pivot element. Everything in pivot row is divided by the pivot element. So minus 2 divided by 5, 50 divided by 5. Everything in pivot column is divided by minus the pivot element, so by minus 5. So we divide all values by minus 5. Then we could start with the rectangle scheme. But similar to our last recalculation, we have a 0 in pivot column. So we can copy this row as is. So those remain as is. We only have to focus on those up here. In this case, the first thing I would do is consider this value. If we do this, we have the respective rectangle here, and we would calculate 25 minus 15 times minus 2 divided by 5. Well, minus, 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 3 minuses, 2 cancel each other out, remaining with 1 minus. So 25 minus 15 times 2 divided by 5, which is 25 minus 6, gives 19. So now both of these values are positive, meaning we have arrived at the optimal solution. We have arrived at the optimal solution, meaning we do not have to calculate these two values because we do not need them. This value, for sure we do not need. This just gives us an information on our constraint x3. Well, we can calculate this, we could interpret this, but not necessarily do we have to do this if we're just interested in the optimal solution as such. If we were to calculate these two values, for the 0 here, we have this rectangle. For the 14, we have this rectangle. So 14 would be 14 minus this times this divided by this. What we have to do is recalculate this value here. So we have 625 minus 15 times 50 divided by 5, which translates into minus minus gives plus. 15 times 10, so 625 plus 150 gives 775. Well, this concludes the exercise more or less, but how do we actually interpret the result now? Well, everything up here has a value of 0. Everything here has the values as given on the right-hand side. So our optimal solution is x1 is 10, x2 is 25. Well, x1 was social media ads, so we have to get 10 social media ads. x2 was magazine ads, so we get 25 magazine ads. And then we get this result for our objective function. Now we have to think back. I said, well, we make the objective function a bit easier by just shortening the coefficients by a factor of 1000. So here we have to readjust the value by the factor of 1000. So we do not have a profit of 775, but we have a profit of 775,000 because we have to multiply this by the factor of 1000 again. Well, so far so good. One final comment. x3, 4, and 5 represent my constraints. My constraints insofar, which can be interpreted that, well, all the parts up here have a value of 0. So in other words, the values up here, which are constraints or represent constraints, are fulfilled with equality. So in other words, this described the restriction that we do not have or cannot have more than a certain number of magazine ads. So we actually got as many magazine ads as we could. This was the constraint regarding our advertisement budget. So we spent every dollar in our advertisement budget. This constraint was for social media ads. Here we have a value which is not 0. So here we have some buffer. So theoretically, we could make up to 4 more social media ads, but they will not be making our profit increase. They make the solution not in any way better. That's why we go with maximum number of magazine ads and fill up the rest with social media ads. And well, that's then about everything I could get from that table. So I hope you enjoyed this session. I say goodbye and see you next time.